would like to introduce the speaker first. Today we are very happy to have Chun from Wayne State University to give the RHIC BES seminar. Chun got his PhD from the Ohio State University in 2014, and then won the APS Deservation Award in Nuclear Physics. And then he was a postdoc fellow in McGill University and a Goldhaber fellow at BNL. He got a faculty position at Wayne State University in 2018, and he also became the research fellow at RHIC BNL Research Center. And recently, he got the DOE Early Career Award. Chun is mainly working. Chun actually working on various topics in heavy ion collisions, including hydrodynamics, flow, photons, BES scan physics, machine learning, and so on. And today, he will give our talk on Bayesian interference. He will give a talk on Bayesian interference of QGP properties and 3D dynamics from BES scan data. Chun, please.
Okay, thanks a lot for the introduction. Today, I'm happy to give a presentation about our recent work of doing Bayesian inference using 3+1D hybrid simulations, especially try to understand the energy scan data. You can find most of the results that we're showing in this archive preprint that we posted last week. And you can feel free to ask me questions either during the talk or after as well. So let me start with a brief introduction. So the goal for heavy ion collisions conducted at various energies will help us to understand or study the phase structures of the QCD in different temperature and chemical potentials. So here in the middle plot, it's basically a list of few of the experimental programs from highest energy at the Large Hadron Colliders to the BES scan at the RHIC, and also future collisions at the FAIR and also hardest. So basically, if you look at the evolution of the fireball created in those collisions at the mid rapidity, you find phase trajectories going through the phase diagram in different chemical potential regions. And by combining those observables at different energies, it will really help us to understand how does, say, the phase, like thermodynamic properties change as a function of chemical potential. Like we want to find, understand how the speed of sound changes in terms of temperature, chemical potentials, as well as search for a potential critical point, and also associate the first order phase transition line. And also beyond thermodynamics, we also would like to understand how the transport properties of fluid changes from the 0 mu b to finite density, namely how A of S and Z of S changes the functional chemical potentials. At the finite baryon densities, we can also looking at the new transport coefficients like diffusions for conserved charges as well. So the goal to actually study or model heavy ion collisions in different energies is one of the approach is try to extend the current successful framework from high energy to low energy. So at the high energies, we have somewhat well-separated phases from initial state to the following. So at the early times, we have systems going through some rapid pre-equilibrium dynamic phase about 1 Fermi over C to evolve close to near thermal equilibrium where hydrodynamics start to apply. Then the majority of the systems was spent in this fluid dynamic phase at high energies, and eventually when you go to dilute hadronic phase, it switch to hadronic microscopic transport approach to describe the dilute phase of the late stage. So this hybrid framework of sandwiching hydrodynamics with initial state and transport actually works really remarkably well in describing observables that measured at the top RHIC and LC energies. So, so want to extend this paradigm or this kind of framework to low energies. So one of the challenge in the energy scan program is that just from the kinematic constraint, that the longitudinal Lorentz contractions between the two nuclei become finite and no longer to be negligible anymore, as you can look at the 20 GeV versus 19.6 GeV, where if you reduce the collision by a factor of 10, you start to see that a finite extensions of the nuclei along the longitudinal directions. And this means that the initial stage and also pre-equilibrium stage will extend its lifetime, not only confined about 1 Fermi, but it could also extend to much longer and also interface with hydrodynamics, which means that the collision happened earlier, you would expect they thermalize or hydrodynamize faster, while the end of the nucleus at the two ends are still kind of incoming and haven't collided yet. So there's a kind of overlap between initial state and hydrodynamics that you need to deal with at these lower energies. And we also, at the meantime, would expect that the hadronic transport phase become more and more important because the systems no longer has a dominant hydrodynamic phase, maybe only short-lived, and then a majority of the phase space is spent at the dilute hadronic phase. So indeed, in order to deal with the first kind of complexities generated in these low energy collisions between initial state and hydrodynamics, you actually need to simulate the hydrodynamic, initialize the hydrodynamic field with with dynamical source terms generated from these initial conditions. So as a cartoon, so you think about the finite thickness of the two nuclei overlap in this light cone diagram. And then when you have this overlap between the two nuclei, this is the regions where you should start to think about generating source terms for energy momentum current, as well as barrier and charge sources for those hydrodynamics. So let me probably just show you one of the numerical implementations of this such kind of design. So here we have two nucleus start to come in to collide with each other. One is marked as blue and the other is red. And this is 0 to 5% go-go collision 19.6 GeV. So as the system evolves, you can see that the nucleus start to melt and then they produce the hydrodynamic median, and after that you will have a 3+1D expansions. So I expect that if you are not have very good internet connections, you may not see this movie very well, but I will try to post this with an external link after the talk so that you can actually access this movie file if you want to use in your future presentation. Anyway, so the numerics kind of frameworks that realize this type of simulations that we're using is so-called IEB music framework. So this is a framework that has been developed for a few years since I graduated from Ohio State. So I still use the IEB kind of name because we have the IEB Vishnu that co-developed by Woody and Hui Chao. And this is considered as a more generalization of the framework to 3+1D and attack more challenging kind of systems in 3+1D. So the main ingredients can be summarized in this chart flow. The takeaway is that this is an open source framework, which means that everything is open source. You can download it from the GitHub repository and you can run it on yourself. To all these different configurations of the models. So here, I think the what is unique for this IB music framework is that we have the state-of-art IP Glasma plus effective kinetic theory to simulate high energy collisions where we can assume Boos invariance. And this is particularly useful when we're looking at the top RHIC and CNG simulations. For RHIC BNU scans, we developed this 3D Glauber model plus these dynamic initializations I just discussed about and connect to hydrodynamics and then do particleizations, hadronic afterburner, etc., and compare to data. So the full event generator is event by event. You can run everything as they are, and then compare up to the experiments with apple-to-apple comparisons. So this is the open source framework, and also and would advertise that we also take advantage of the free computing source that provided by the Open Science Grid. So if you look at, say, the last 90-day running on the Open Science Grid, you can already see that two of the group actually is on the top three of the user in the last 90 days, and even that Zhang Yong's group from Stony Brook even beating us at actually is the top one user using our framework to generate simulations for RHIC and LHCs. So this means that not only we can use the framework, any of you that have access to Open Science Grid can use can take advantage of running our framework and doing heavy ion simulations with this free computing resource. So now let's go into the kind of the model details. So for the beginner scans, we developed this 3D global model trying to simulate the dynamics in the longitudinal directions. So we start with basically a transverse geometry that based on the conventional global model for the wounded nucleons. And then in each of the nuclear collisions, we consider about valence quarks degrees of freedom, where their longitudinal momentum is sampled from the PDF. So we impose our extra constraints that the sum of the x for the 3 valence quark has to be smaller than 1, such that the sum of the longitudinal momentum for the 3 valence quark hotspot is smaller than the total longitudinal momentum of the incoming nucleon. So once you have that implemented, you can actually model individual nuclear collisions in the heavy ion collision. So if we have a nucleon pair going in, when they collide, we first go to the pair rest frame and pick up a pair or multiple pairs of the hotspot from the valence quark, and each of those pairs can actually decelerate with string tensions along the longitudinal directions. So what we do is we basically looking at the energy lost from these collisions, and then deposit this energy and the momentum as a longitudinal plateau in the space-time rapidities along these A to S directions. And the hotspots final energies will be deposited as 2 Gaussians at the end of the strings. So with energy deposit, we can also deposit baryon charges associated with those hotspots. So either the baryon density can be deposited as the Gaussian at the string ends. We can also allow them to fluctuate to the middle rapidity due to the fragmentations of junctions like there.
Quick question.
Yeah.
Quick question. Did your movie show these valence quarks, or did it show positions of nucleons?
The movie shows the position of the nucleons. Yeah.
Thank you.
Mm-hmm. Yeah. So yeah, so this is a little bit of details about the initial state setup. The takeaway message from this new kind of 3D initial condition is that we can impose conservations of energy, momentum, and net baryon density from the incoming state before the collisions to the hydrodynamic fields, which you can also calculate those quantities, and they actually conserve between initial state and hydrodynamics. So this is only doable when you go to the full 3+1D simulations, where you know that the total energy has to be equal to the incoming collision energies if you integrate over the space-time directions. So in the following Bayesian analysis, we want to really extract from this initial state is basically a way to quantify the initial state nuclear stopping. So that's one of the questions that both theorists and experiments are interested with, as how the nuclear stopping is conducted as different collision energies. So in this model, we directly implement this as a model parameters in this model as these Y loss parameters. This is the rapidity loss for each individual coming pair of the hot partons. So we parameterize this Y loss as a function of the initial coming rapidity in the pair rest frame for the initial hotspot pairs. So in the Bayesian analysis, we use a pairwise functions, essentially just looking at just parameterize the Y loss at the three different incoming rapidity, and then just linear connect them in between for the parameterizations. So I also plot the beam rapidity for 7.7, 19.6, and 200 GeV as guidance, so that you can see that if I'm looking at 200 GeV data, I mostly will constrain the Y loss rapidity at the 6 and also 4 will actually influence the 200 GeV point. And then for 19.6 and 7.7, everything I would expect more dependencies on changing these two parameter points. And the constraint and experimental data would constrain more or less these rapidity windows. On the top of this Y loss, we also include some fluctuation away from the mean value, which is indicated as these solid values. So we can introduce a variance for this curve, such that in every individual collisions, we are not always have the same rapidity loss, but it can fluctuate with a given mean indicated solid line and the variance indicated as sigma Y loss. You may notice that the band start to shrink at the low rapidity. That's because that if I use the Gaussian with the fixed mean, that the value of the Y loss can be exceed the limit where it's bigger than the initial rapidity, so that we actually have a transformation.
Hello, Chun.
Yeah.
There is a short question from Jorgen.
Yes.
Jorgen?
Yeah, I do remember from Witt's analysis, Witt-Buscher's analysis in PA, that Y loss used to be exponential, so flat in Z and exponential in Y. You seem to, so you just take a fixed value and then a Gaussian around it. Did you try an exponential?
Exponential in Y.
In Y, which is flat in Z.
We haven't tried, but I don't think it will be compatible, because the end extractions we find is much like really flat kind of function.
Maybe I remember wrong, somebody else might remember, but I have in mind that it's exponential measured in PA and PP. Okay,
yeah, that one we didn't look at, but also here for now we only using the heavy ion data, but in principle we can also start to look at the PA as well, see whether we would get any difference or not in there. Okay, this is the parameterizations, and we have 4 parameters essentially to control the initial, to try to quantify the initial nuclear stopping. And then once we have that, we will go to the hydrodynamic phase. So the hydrodynamics, we first need to solve the hydrodynamic equation motions with the equation state. So here, we don't want to introduce too many model parameters in the first Bayesian trial of this Bayesian analysis. So for the equation state, we use the lattice QCD-based equation state extrapolate to finite chemical potential. So for this NUS equation state family, but we impose 2 constraints. So the local strangeness neutrality, and also the electric charge is equal to 0.4 times the baryon charge, which is suitable for the go-go collisions with their Z over A ratios. So at the finite density, this lattice equation state using the susceptibilities calculated from lattice, and then with the Taylor expansions to extrapolate to finite density, and then at the lower temperature we match to the hadron-Lorentz gas with these formulas. So this is somewhat we fixed in these simulations. We didn't change it, the equation state in the high mu B regions for this study. What we do introduce as model parameters is the chemical potential dependence on the shear viscosities indicated on the left, and also parameterization for bulk viscosity on the right. So first, for the shear viscosities, we know that from experience of two-dimensional Booth invariant Bayesian analysis in the high temperature or high energy calculation, that effective shear viscosity is usually sufficient. We don't really can constrain where the temperature dependencies right now. But so in this case, in order to save model parameters, we just parameterize AWS as a function of chemical potentials in 3 different chemical potential values, and then linear interpolate between them. And the temperature, you can think about these 3 values are effective AWS as a function of temperature, which is along the another axis. However, the bulk viscosity usually exhibit peak structures around the transition region, so we still keep that feature in there. So we basically have 4 parameters to parameterize the bulk viscosity as a function of temperature as some asymmetric Gaussians indicated as here. And the way the trick we want to do in the next is basically try to relax this parameterization for different energies so that we can get some hints on the mu-b dependence on bulk viscosity after we train the emulator. So we'll discuss about more details about results with.
你弄好了吗，乖乖？查一下，或者还给我啊。
Is there any question? Okay.
I have a question.
Yeah, go ahead.
So just to make sure, so the shear viscosity is temperature independent, but is parameterized with a mu-b dependence. The bulk viscosity has a temperature dependence, but you do not allow for mu-b dependence.
At this one, no, but because we want to not to be too ambitious.
Yeah. Just want to make sure.
Otherwise, the parameter, the model parameters just explode in terms of numbers. Yeah. Okay, so this is a summary of all the model parameters that will vary in this study. So the blue, I will not go through each one by one, but I just give you a brief kind of intuition is that everything marked as blue is from the initial state. Try to basically model the both transverse and longitudinal shape of the energy density profile and the baryon densities. And then the green one is the parameters in hydrodynamics, about 8 of them. 7 of them are parameterization for shear and bulk viscosity, and also we have a switch energy density, where we switch from hydrodynamics to transport at the fixed energy densities at the finite densities. So in order to carry out the Bayesian analysis, of course, the 3D model is very slow. We need to train a model emulator to calculate or estimate the outcome of the model as fast as possible when it goes through the Monte Carlo Markov chain. So this is a 20-dimensional model parameter space. What we do is we have a design of 1,000 training points in these 20 dimensions using Latin hypercube. And then with this, for every training point, we run this amount of minimum bias simulations for hydro. So for a 200 GeV, we run 1,000 minimum bias simulation for each of the training point. For each of the hydro, we oversample about 1,000 hadronic afterburner simulations, such that we get enough resolutions to calculate QM vectors, the flow vectors from the particle samples. And for the lower energies, we increase the statistics to 2,000, where we find that there's more fluctuations in this lower energy compared to 200 GeV. So we increase the hydro events to 2,000 for minimum bias at each training point. For each hydros, because the overall charge particle multiplicity is lower at those low energies compared to the high energies, we also increased oversampled factors in the EuroQMD events to 4,000 for 19.6 GeV and 8,000 for 7.7 GeV. So still this is a significant amount of computations we need to carry out this training to generate this training data set. So we improved the numerics over behind the scenes so that each of the 3D runs take about 1 hour to finish. So if you add up 1,000 training point with all this number of hydro events, it's add up to be about 5 million hydro events and take about 5 million CPU hours. And all of them are actually delivered by the Open Science Grid and for these training data generations. So once we generate those data, we try to compare, at least for the first iteration, is with the experimental data summarized on the right-hand side. So in total, we have include about 604 experimental data points. They include the centrality dependence of the particle productions of identified particles, the function of centrality, at the rapidities from star measurements, their mean PT, and also charge hadrons V2 and V3. So the left column is all from measurement from star at the mid rapidity y equal to 0. And also in addition, we want to explore whether the rapidity dependent measurements can actually impose additional constraints on the model parameters. So we include the Phobos early measurements of the dn charge d eta and also V2 as a function of eta in the analysis. So another way to show you the landscape of the model parameters versus experimental observables can be shown in this colored figure, where the model parameters is listed vertically here. These are 20 of them here. And then horizontally, you have about 604 experimental parameters listed in the horizontal axis. So I want to show you that each individual of this block here actually contains multiple centralities. There's about 7 centralities in each of those blocks. Although you look at them as a one single, look like a single pixel, but there are 7 of them inside here. But also you can see that since the colors are very similar, which means that they are really correlated. So as a function of centrality, they are really correlated with each other. The color coding in this figure is reflect the covariance between the model parameters and the experimental data. So if you see a really bright red or very dark blue, this means that there's a very strong correlations between the model parameters and the certain model observables. So the red means positive correlations and the blue means negative correlations. So let's basically digest a little bit on this correlation plot. So if we first just look at the rapidity loss parameters, which control the amount of energy deposit in the mid rapidity or along the rapidity directions, you would expect this to be very strongly correlated with particle yields. And this is actually seen from the training data. So you can see that if I look at 200 GeV go data of identical particles, I see very bright red that sensitive to the rapidity loss at 4 and 6. And this is because the beam rapidity is around 5, which is in between these 2 parameters. And you see there's almost no sensitivity to the right loss at the 2, where this incoming collisions doesn't access at 200 GeV. However, if you go down to 19.6 and even 7.7, where the beam rapidity is between 2 and 4, you can see that the red sensitivity show up in this multiplicity particle multiplicity to those observables. But that really makes sense, a lot of sense. And the second is if you look at the Phobos data from the rapidity dependent observables, you can see a positive correlations in the mid rapidity and the negative correlation at the forward. So this is really coming from energy conservation. So if we stop the nuclear with a larger stopping power, you have more energy deposit in the middle, and naturally will have a negative, less energy in the forward direction. So you have positive correlations at the mid rapidity and negative correlation at the forward. But that also makes a lot of sense in our expectation that this correlation is actually visible in the training measurements. We can also take a look at the response of the variable response to the shear viscosity. So here, first of all, compared to the previous plot, you can immediately notice that the color is much lighter in this case, which means that the viscosity actually shows a much less response to the observables compared to the initial state repeated loss. So, however, you still see lots of familiar phenomena. For example, the shear viscosity at 200 GeV has a positive correlations with particle yield. And this is really telling us about the viscous entropy productions during the simulations, which give you a positive correlations. It also gives a positive correlation to the identified particle mean PT because the shear viscosity try to speed up the transverse expansions while slow down the longitudinal expansions in 200 GeV. So you can actually see that basic physics in these correlations. And of course, the shear viscosity reduced the anisotropy so that you see the negative correlation to V2 and V3 in the charged particles. What is interesting is that if I want to draw your attention to the Vn as a function of eta at the phobos at 200 GeV, you can actually see that it actually shows also negative correlations even at the finite chemical potentials that that also will show up in there. So this will also be interesting to see whether in the next that how the repeat dependent V2 actually give us extra constraint on the mu B dependence on shear viscosities. So last is basically we can look at also similar with bulk viscosity. Here are the parameterizations with these asymmetric Gaussians. Mostly we can actually look at the maximum, the peak values of this bulk viscosity. So which means that you can again see the positive correlation with identified particle yield due to viscous entropy productions, reduction of mean PT due to the resistance of the bulk viscosity to the gradient to the radial expansions, and also suppressing V2 with a slightly less sensitivity there. The other observable we find is that if we look at the repeated dependent yield, we see that the forward particle yield actually shows a strong sensitivity to the bulk viscosities, to the maximum bulk viscosities, mainly because that this is in the dilute regions where you would expect more of the fluid cell going through the peak of the bulk viscosity and generate more entropy there. So basically, looking at this covariance plot between model parameters and experimental data already tell you a lot of physics you would expect between how the model responds to the observables, or how the observables would tell you about the physics in the quark-gluon plasma. So, but looking at that plot is not that fun. You need to really spend a long time to actually digest. Another way to actually play around is to use this interactive web page that we build up for the model emulator that we train. So basically, you can vary all 20 model parameters and really to see in real time the changes in the observables. So maybe let me just basically show you as a demo how this looks like. Let's share a new one. So this is basically the interactive website in live. So for example, if I change the Y loss at the repeated equal to 2 to a smaller values, I would expect you can gradually immediately see that you underestimate particle yield for identified particles at 19.6 and 7.7 GeV. And you can actually play around with all different 20 parameters here to actually build up your own intuitions. So this website is another way to help you to build up intuitions about how the model parameter, individual model or parameters response to the observables. So I'll post this link in the chat so that in case you're interested, you can go to this website and play around with yourself. So Let me go back. So with the model emulator trained, so the one step is to first to verify that our simulation is actually effective. So this can be done through a closure test, where we apply the Bayes theorem to a testing model set, where we run the model at some parameter space that hasn't been used in the training, and then try to carry out the Bayesian inference for that. So here, the gray band is showing the prior distributions at the 90% confidence level for the initial state stopping in the left, shear viscosity in the middle, and ball viscosity on the right. The true model parameter is indicated at the solid red lines in these three variables. And then after you do this using the trained emulator and then going through the Monte Carlo Markov chains with the Bayes theorems, you can get the red band as the 90% posterior for these three observables. And you can nicely see that it covers the truth in there, and also extremely that we're happy to see that the constraints on the initial nuclear stopping is very tight. And it shows us that very promising that we can get these observables with a very good confidence with some good constraints on these observables. And also this closure test is also give us another message, is that the choice of these 604 experimental data points are really effective for us to constrain these three variables through these closure tests, if we have good enough statistical errors from them. So now, once we pass this closure test, we want to do the real thing. We want to actually looking at the real data. So here is basically the experimental data that we are looking at. So on the left is the star. From the top is particle yields, dNdy, the function of centrality for Turing GeV 19.6 and 7.7. Middle panel is the mean PT for identified particles, pion, kaon protons, and then also antiprotons as well. And then lower panel is the V2, V3 from star measurements for the three energies and rapidity and the function centralities. On the right panel is basically Phobos measurements of dNd eta for a few different centralities for Turing GeV, 0 to 40% V2 the function eta, and then 19.6 GeV dNd eta at several centralities. So the lines are the prior, which mean that they are the training data that we use to train the emulator, the 1,000 training points. And then once we do the Bayesian analysis, you can nicely see that the posterior kind of shrink down and actually constrained by the experiments. And you can also nicely see that the width of the band is comparable with the experimental errors for most observables. However, we also see there are some tensions as a function of centrality, that the V2 and V3 may have some tension in the lower energies, which we can further looking at in the future. But overall, you can see that this is the way to carry out this Bayesian analysis. And we get a reasonable fit to all these observables in our considerations. And then once we have that, we now turn around and then try to look at the constraint on the physical observables. So first we want to look at is the nuclear stopping. So the nuclear stopping we can do is one by one. We can first just only apply the go-go data at the mid rapidity. So as you can see that if we only have Turing GeV data, we get constraints around beam rapidity equal to 5 at this part. So this is where the most of the constraint is derived. And then we also see that the value of the rapidity loss is about 2 units at the Turing GeVs. If we further impose the repeat-dependent data from Phobos, you can see the posterior shrinks from the red band to the blue band. There's not much, there's slightly narrowing of the constraint, but not much. This is mainly, I think, because the Phobos data in DN data usually carry much bigger systematic error that doesn't impose any very strong constraints compared to the star measurements. So last but not least, we can now impose the full RHIC and BES data so that from 7.7 is 19.6. And you can nicely see that in the end, the green band is much narrower compared to the posterior prior in the 90%. So we get a very strong constraints on the nuclear stopping, which is indicated this green band here as a function of initial rapidity. So one way to also see is nice to see is that we also put some estimates from Brahms using the net baryon distributions. These are the experimental estimates, points from the estimates. And you can see they are actually nicely in line with our analysis using the constraint from the particle chart, identified particle data. And then they are actually constrained from the net proton rapid distributions. So these two independent analyses sort of agree kind of in line with each other. Okay, now we go to the viscosity. So first is we want to look at whether we can get any constraint on the chemical potential dependence on shear viscosity. So here we first again only apply the RHIC top energy data, which you can see that give a constraint at the zero AWS at the zero chemical potentials between, if you look at difference between the red and the gray. And there's no difference in the finite chemical potential. In this case, we find that if we now impose the Phobos data as a function of rapidity, especially V to the function eta, we not only get a better constraint at the mid rapidity at the zero mu b, but also quite big constraints at the finite chemical potential around 200 MeV. So this means that at the full rapidities, although it is at the 200 GeV, it's actually sensitive to the shear viscosity at the 0.2 GeV regions. And the Phobos data indeed give us a much tighter constraints in terms of chemical potential dependence. And also if we apply the full data sets, we get the green band, which also impose some constraints at even large chemical potentials for the shear viscosity when we look at the lower collision energy from star. So overall, if you look at the green band, you can sort of see a kind of increasing trend of chemical of ALS as a function of UB from 0 to finite chemical potentials. So from here, we kind of infer that at least 90% confidence level, the ALS in the coagulant, the effective ALS in the coagulant plasma increases as you go down to finite chemical potentials. So here is another exercise we can do is basically to ask, what if I just use the full RHIC BES data?
Can you tell us what is the temperature you use there for AWS?
This is temperature independent. So this is effective temperature independent. So every mu b is basically a effective constant AWS.
Mm-hmm. Okay,
so
thank you.
We didn't extract the two-dimensional yet, but that's the next step. Yeah. Mm-hmm. So one of the questions interesting to ask is, what if I just use the full BES data from star at the mid rapidity? How far can I go without imposing any rapidity dependence measurements from other experiments? So here is the posterior by imposing just RHIC BES data for initial charge stopping and the shear viscosities. So what you can see is that comparing the pink line here versus the green line here, they are quite similar in nuclear stopping. This means that the identified particle yield and mid rapidity already do a good job to constrain this rapidity loss from the initial state. However, on the other hand, if you look at the AWS, you can see that at the 200 GeV mu b 0.2, actually the rapidity dependent observables are actually more important to actually help us to get more constraints here.
Could I ask a question?
Yeah, go ahead.
Is your rapidity loss determined mainly by energy conservation, so by how many energy you deposit, or is it determined mainly by the baryon distribution in rapidity?
It's about the energies. It's mainly
energies.
just, yeah, for pion and kaon so yeah, for pion kaons we can already get this.
Okay, so it's really just energy conservation. You say I find X particles at mid rapidity, it comes from the beam, so I lose.
Yeah.
Okay. Okay. Okay.
Okay. Lastly, now let's go to the bulk viscosity. So as we said, yeah, go ahead.
So you said the beam energy scan was not as efficient in constraining the shear viscosity as including the Phobos, but that's because the beam energy scan data that you used didn't use any rapidity.
Yeah, correct. This is only mid rapidities.
So this is really the constraint from the rapidity dependence of V2 from Phobos, which drives it.
Yes.
Okay.
Okay, lastly, we can look at bulk viscosity. So bulk viscosity, we first parameterize a function of temperature. So we can look at just at the 200 GeV, the constraint. So if we look at only the mid rapidity data, this gives me the red band. And then if we impose the Phobos measurements at the function rapidities, we get actually a slight increase of the posterior to the blue band here. So we see that somehow this particle yields at the 4 rapidities from Phobos actually give you a little bit more constraints to these observables. This can be traced back to discussion about the covariance between model parameters and observables, and identify this as the particle yields at the 4 rapidities to give you extra constraints. So what is more interesting is that now we can play a game that we can set the parameterization of bulk viscosity to be free for each individual energies, and try to understand effectively how does this bulk viscosity changes with effective chemical potentials that are probed by these 3 energies. So this is basically a kind of cheap way to, without running extra calculation, but to try to get some hints on the mu B dependence on zeta over S. What interesting is that we find is the 200 GeV is showing this red band, and 19.6 is this blue one, and then the 7.7 is the green one. What's interesting to find is that the 200 GeV and 7.7 are quite close to each other in terms of the peak and also its value. However, the 19.6 actually disfavor a small bulk viscosity in the transition regions. So if you think about in these 3 energies, this kind of is a non-monotonic behavior. If you think about this 200 GeV is about zeta of S around mu B equal to 0, and 19.6 is around 20 GeV, and 7.7 is even large chemical potentials. So somehow there's a kind of a bump of bulk viscosities at 19.6 GeVs. So to illustrate this a little bit better, because this is a 90% posterior regions which they overlap with each other, you can basically subtract zeta of S from 19.6 to the 2 energies. And this is plot on the right-hand side as a function of temperature. And this subtraction is actually done sample by sample in the posterior, so that they actually take into account the covariant variations by other model parameters. So you can clearly see that there's a bias of the distributions at 0.15 and 0.2, where all the distributions is biased towards to the positive side. So this can be also seen compared to the high temperature. You can see there's almost symmetric contributions, which means that there's no preference of these to be positive or negative. But we clearly see a bias of the posterior distributions that hint there's a larger bulk viscosity in 19.6 over the other 2 energies. So this could be a hint that zeta of S could be just have some interesting peak structure around, say, finite chemical potential around 200 MeV. And also it could be saying that it relate to the equational state, that our equational state at a finite mu B may not be accurate enough, that it could be a softening around 200 GeV, and also maybe a hardening of the equational state at even larger chemical potentials, which could also reduce this monotonic behavior of zeta over S. So this is something that we found is really interesting coming out from the analysis, and worthwhile for another more careful treatment in the next runs to get better constraints on this. So maybe let me summarize my talk. So what we show you is basically we carry out a Bayesian inference using multiple experimental measurements at the multiple energies from the RHIC energy scans, and with event by event hybrid framework. We get robust constraints on the nuclear stopping, and also constrained chemical potential of 8LS, and some hints of bulk viscosity to be non-monotonic around 19.6 GeVs. So we want to mark is that our study is not the final story about the studying of BES scan data, but rather a beginning, because we actually, from the theory side, we eventually kind of reached the threshold that carry out this full 3+1D simulation with Bayesian analysis is kind of affordable, and you can actually do that with a scale about a month or two, and then generate the training data and then carry out the simulation you need. And we want to see that this will be kind of the beginning of to do more quantitative comparison with the BES data and maybe future fair experiments. In the future, we will actually really excited because there's just new data really from the phase 2 BES data, and from the theory side, the next step will be a little bit more ambitious to actually looking at, say, parameterizing speed of sound in the equation state, and go to maybe multiple densities in the phase diagram in multi dimensions, and eventually tackle on the critical fluctuations problems as well. We also plan to extend the 3D simulation to RC energies, where there's a very good quality of data as a function of rapidity. This will help us to understand, say, small x evolutions, the role of nuclear structures in initial state. Last but not least, we want to say that we want to open our also training data to the community in the near future, because we know that the generating data are really expensive, and having those data shared with the community will also engage us to have more collaborations from different groups to develop robust and efficient statistical analysis that improve the simulations in the futures. That's all I want to say. Okay, thanks.
Okay, thank you for the talk. Time for questions.
Can I ask a question?
Uli,
Okay, can I ask a
Uli,
question?
please.
Yeah, I got disconnected for a short while at the beginning. So if you could just quickly repeat what you use for the initialization. So you use a gradual feeding of the hydrodynamic fluid by this breaking of the strings, right?
Yes.
So what kind of longitudinal flow profile does this result in?
This is, yeah. This is still, I think, longitudinal profiles is still quite close to Bjorken. It just basically you have an energy density profile to be non-trivial, to start with. But I think from our current analysis, this looks like not too far from the Bjorken expansions.
Okay, but that means that you at early times you have to contend with the large temporal gradients that Bjorken flow has. And how does your code handle these?
No, so we start the hydro around like 0.5. We don't start with 0+. So there's no like 1/tau singularity there.
So what happens between what happens between tau equals 0 and your
so between 0 and 0.5, it's basically just one-dimensional deceleration according to this formula. And then we put in some, we have one parameter in the model to take into account some possible transverse expansions of the transverse preflows during this time. So this is one of the model parameters we introduced.
So that's interesting. So you have this longitudinal deceleration, but then this still leads to a Bjorken type of flow once you have
so that statement is, well, that statement I think still need to check a little bit more quantitatively, because what I was saying is mostly coming from the recent calculation of vorticity, etc. That's very close to the Bjorken scenario from this model. Yeah.
Okay.
But I would still need to quantify a bit more. Yeah, I would say.
Boris, please.
Yes, hello. Thank you. So I'm wondering about this stopping and the rapidity loss, because I'm trying to think about that as a universal effect. So would it be reasonable to also apply it in proton-proton collisions and see what rapidity distribution you would get, or is it completely something different in proton-proton?
So yeah, so we
completely
tried.
different.
So what we did is we didn't do the Bayesian analysis with that, but we have a early paper where we basically using a single parameterization of this curve. We can match the PP multiplicities actually. You know, we can do PP, PA, and AA with a single parameterizations.
But as I said before, in PP, the event-by-event distribution is very different. So the averages actually are similar. The average energy loss is about 2 units as well at high energy, but it's an exponential distribution. So the most likely value is 0, and the average is 2, and it's exponential in Y, which means it's flat in Z. So
yeah, so what we do is we did I think for PP. What's really important is this sigma y. So it's the width here we control. So here is like has a Gaussian fall off in our case, but we tune that width to the multiplicity distribution PP. That width is actually.
But it's not an average value with a Gaussian. It's exponential with a maximum at 0 energy loss, at 0 Y loss.
That probably is not consistent with this model.
In PP, exactly. That's why I say in PP, you cannot use your model in PP.
No, we tried PP that at least for particle yield, we can get some.
Of course, you can always, that's why I asked before. What you do is you just look at dN dy, and then you say, on average, I have to lose so much energy. But then you don't describe the dN dy distribution of protons.
No, we do. Proton
in PP.
Proton we should take a look at, yes. So that one we need to take another look. We didn't look at proton yet. We only look at the particle, like charged particles. Yeah,
exactly. But if you, of course, want to describe it event by event, the rapidity loss, which should tell you where the proton ends up, the proton ends up most likely at the beam rapidity and not shifted away. So, I mean, in AA, because you fold many exponentials, you start getting an average with which. Once you fold many exponentials, somehow it becomes Gaussian, maybe. But it's not applicable. You cannot apply it straight away to the rapidity distribution of protons in PP.
We can try your exponentials later in the model, see what come out. Then we can do a closer look at PP.
But you have to do it per collision, and then because you have many collisions, it does resemble more your model. And also another question, but maybe first I wait my turn.
Yes, you can continue to ask.
Okay, so this was about the initial longitudinal distribution of energy. So in your model, you somehow probably simulate some fluctuations of the energy density profile along rapidity.
Yes.
Now at very high energy, at LHC, one of the most sensitive observables is the decorrelation of V2 as a function of rapidity gap. Are there any measurements of that at RHIC energies? And if so, then you should, and then you should compare to that. That would be very interesting.
So there are measurements at 200 GeV and also I think 19.6. And 27 GeV for the rapidity correlations. So at the current stage, we didn't include in the Bayesian because they are still very statistical demanding. They require a lot more events per training point to get them under control. But they can be, I think they could be doing in the future. But just taking some kind of posterior value, and then we can actually start to look at how far whether we are completely off of the data or not. But I think we are quite close to the measurements as well. But I agree. So this will be a more additional constraint that we can use in the future when the numeric is further improved to get more statistics in there.
Okay, I think there is Feng have questions from the chat box. Feng, can you ask yourself?
Yes. Hi, Chun. Yeah, very nice to hear from you, and it's very interesting talk. My question refers to the effect of afterburners, since you have discussed the influence of initial stage, right? You have also discussed the influence of the hydro parameters. And have you ever, maybe in future, do you plan to consider the influence of afterburner as well, since it refers to the scroll to S dependence of your bulk viscosity, because at lower beam energies, the influence of afterburner might be important, right? So for example,
you're talking about mean field, right? Mostly mean field.
Yeah, it's mean field, yeah.
So
you can also
I think those part one of the interpretation I have is because we are doing these hyper simulations, the high density regions of the collision is taken care of by hydrodynamics, which the mean field as is most reflecting to the equation state. And then we only use the afterburner when the system is dilute enough, so that I would expect the mean field effects to be small. Then the pure transport, right? If you think about pure transport, you also try to simulate a dense regions with transport. Then you need the mean field effects, trying to change the equation state, etc. So I think in the hydro plus transport kind of hybrid, the mean field could be minimized, but still worthwhile to check in the large mu B regions whether that's true or not. But from my feeling is that the hydro take care a majority of the mean field effects in these hyper simulations. Of course, this simulation has a kind of a disadvantage compared to pure transport, is because you need to do the Cooper-Frye, right? You need to translate the microscopic degrees of freedom to particles, which has a lot of theoretical uncertainties. But I think large part of mean field effects is taken care of by the equation state in hydro. So if you have some attractive interaction in the transport phase, I guess this is related to basically modifying, say, equation state large densities in the hydro, and then use them as a feature to constrain whether the lattice extrapolation, how good the lattice extrapolation is or not.
Okay, thanks.
Okay, thank you. Li Pei, please.
Yeah, thanks. So I have a question about your constrained repeated loss compared to the experimental estimates.
Yeah.
So if I understand it correctly, so your constraining is mainly from the charge particle multiplicity, right? It's related to energy loss.
Yes.
Energy deposition. On the other hand, the experimental measurements are mainly from the net baryon distributions in rapidity. So I mean, you see the agreement, but what does this agreement imply about baryon stopping?
I think the front experiments is an estimate from the baryon stopping, like a net baryon distributions. I think the agreement here may just hint that the energy stopping and the baryon stopping are roughly okay enough that they don't, at least in the low energy, maybe they're okay. Already just saying that you cannot distinguish there may not be some extra baryon stoppings in there.
But I mean, the net baryon distribution is very different from the charge particle distribution, right? In some sense.
Yeah. Yes. Well, but the stopping power is basically extracted here, right?
Okay. So is it does it imply the energy deposition is highly correlated with baryon stopping?
No, in this model, no. It's still they kept to be independent, but somehow these constraints are still in line with each other.
Okay, thanks.
Okay, Uli,
Yeah,
please.
I wanted to come back to the preceding question with the afterburner. You had one parameter in your model, which was the energy density at which you do particle when you go to high energies, the value of that switching energy density or switching temperature is highly controlled, strongly controlled by the chemical composition of the final state. So it really is at least if we assume that particleization happens in chemical equilibrium, then that constrains the yields that you measure, constrains this temperature. What is it in your case that constrains the switching temperature?
That's the same idea. Yeah, just at the finite chemical potentials.
Okay.
But you
say that happens. But you say that happens. So you say that when you take that into account, you are driven to an energy density for the switching that lies considerably in temperature below the phase transition temperature.
Well, so the usual E-switch we extracted about is around like 0.3, 0.4 GeV per Fermi cube. So it's like about twice of the saturation density. So in that case, I'm not sure that the mean field will be really important. But it's worthwhile to check in the future. But in this model, this E-switch is again purely driven as done in the high temperature side is due to the chemical balances of protons. So the proton yield kind of driven what value this E-switch is.
But when you take your equation of state and you look at the inflection point to localize the phase transition temperature, what's the energy density there?
So the finite μB phase transition temperature kind of follow the constant E-switch. So basically we are actually just below that switching in all μB. That's why I use the constant energy density to switch.
Okay,
because
so
you seem to similar kind of curvatures.
You seem to be making simultaneously two statements, which I think, which in my mind are somewhat contradicted to each other. You say the switching energy density that you are driven to is consistent with the energy density at the phase transition, and you're saying it's dilute enough that you don't have to worry about bulk viscosity. I always thought
No, I mean, I'm not worried about the mean field in transport.
Isn't that related to the bulk viscosity? I mean,
I don't know yet.
If you have no mean field, if you have no mean field, you should also have very low bulk viscosity. I thought maybe too naively that this was the case.
Yeah, it could be. But that's my expectation, but it could be wrong. Yeah.
Okay.
Yeah.
Okay.
志东 please. 杨志东。Hello, we didn't hear you. Okay, I think there is something wrong with his microphone.
Can you hear me now?
Oh, yes,
Can you hear me now?
Oh, yes.
Sorry, I think there's something wrong with the microphone. Yeah, really nice talk and really interesting result. I have a question. So can you go to page 28?
Yeah.
Can you go to page 28?
Yeah, I'm at 28. Maybe just on
okay.
on the web. Yeah.
So so your shear viscosity is effective shear viscosity. Yes, there's no temperature dependent. Yes. So my question is for zero chemical potential. It seems the value is too small because we know from other Bayesian analysis results like JScape and the recent Mega result. So they provide temperature dependence of 8 OS at a zero chemical potential. And if it's effective 8 OS, I think we expect the value of 8 OS should be I think should be a little bit larger. Because
this is the constraint, but I would say that most of the Bayesian from the high energy part cannot really exclude the constant 8 OS. And also this one is kind of, you can understand the effective one, right? As you said. But this is what
I
we get from this model. Yeah.
Yeah, I mean,
We
it
also
is
call
possible
it
it's constant shear viscosity. So, but I wonder, it seems the value is too small, because based on my impression, even if one use effective 8OS at zero chemical potential, I think the value should be like it's about like 0.16 or 0.2 or something.
That depends on the initial state. So how much initial state fluctuation included in there, I would say, right? So for this particular model, like Glauber, you probably prefer a smaller viscosities.
Okay, and another question is, so you use parameterization for the mu-b dependence of this effective 8OS. So have you tried like just extract the 8OS for each kinetic energy? Like for example,
This we can, well, that's kind of a way that so
because
the
I worry about
is,
the parameterization may have an effect. Like for example, for the 18.6 GeV, you can just like constrain the effective 8OS at this energy.
So the way we can do it, but really the physics is that 8OS should not depend on root S. It's basically a quantity that depends on the thermodynamic variable, like temperature and chemical potentials. What really you want to do is basically look at the mu-b dependence. So if you go to the square root of S, as we did the estimation for bulk viscosity, it kind of is a first step towards estimations. The real game is you want to just parameterizing T and mu-b and then try to constrain it with the global data. The other thing is that if you extract a constraint with a fixed energy density, fixed collision energies, you kind of lose the ability to look at the rapidity dependence, because at the finite rapidities, they do depend on the finite chemical potentials at the finite result, even 200 GeV. So that parameterizing mu-b is really kind of the way to go in the future to extract both shear and bulk viscosities instead of root S.
Okay. Thank you.
Okay, thank you. I didn't see more questions from the audience. Maybe I think we could end the seminar today. And thanks for Chun for the next talk. Thank you, and see you next week.
Thank you. Bye.
Okay. Bye bye.
Bye.